why we open a file and then read from it instead of just reading from it. Like, we could have a different interface that just, you say, read from this file, this block, something like that. And there's a few reasons for that. One is that open tends to do a bit more work than a typical read might want to do. So for example, open might do permissions checks. Open might do an expensive path name traversal. And we really want to support the notion of what sometimes you might call read cursor. This notion that we have a position in the file that we're currently reading from or writing to. And that's that offset I was talking about earlier. So for all those reasons, the interface makes some sense. We open a file, we do this expensive, some expensive stuff, then we give back to the caller a file descriptor, which is a way for them then to read from that file, and we don't have to do the permissions checks already again because we already have done those things at some level. We don't have to do all the permissions checks at least. That file descriptor is sometimes something people call a capability. It's basically something that you hand to a let's say a process that lets it do something. And in this case, what it lets the process do is, for example, read from a file. And of course, there's actually quite a bit of written material about capabilities as a general thing. In fact, there's a whole book by Hank Levy at the University of Washington that you can read, and I think you can download it for free. And it's a pretty general concept. It's a little bit hidden here. It won't be a major focus of our discussion, but it comes up a lot in security or protection contexts. So anyway, we were talking about opening a file, reading it. Of course, at the end of that, after doing open and then doing some number of reads, what you might do is you close the file, and close just lets you basically recycle that particular file descriptor. It makes the file no longer accessible. Now we're going to talk about writing. Writing is a little bit similar, of course, to reading. Here's an example of a file. What we do here is we open the file, and instead of for read only, we open it, let's say, for write only. And of course, you can open a file read write as well, because you might read and write to from and to a file. I'm going to ignore this lseek for a second. But what write is going to do is, well, here we're just writing on a buffer and putting, in this case, the letter B inside of it. Let's see what that looks like. Oh, we see it. Something here with a bunch of A's in it. And in fact, let's make that a little bit shorter, because what's the point of having such a long file at this point? And then let's go ahead and run grow. You can see what happened. We open the file. When we open the file and grow, what happens, of course, is we get a new file descriptor, and the position that we're writing at the file is set to 0. So when we issue this write, we're essentially going to, because the file already exists, we're going to overwrite it. Overwrite that first, in this case, first 2 bytes. So we had a file that had AA inside of it. And then when we were done with this, file 1 had AB. So that's how you overwrite something in an existing file. Now I may point out here we didn't actually even close the file properly. And at some level, in this kind of program, it doesn't really matter if you close the file or not. Closing doesn't do anything other than really recycle the file descriptor. And another way to think about that is when so you could view it as a resource, and you might be leaking that resource. If you keep opening files and you never close them, at some point you'll run out of file descriptors. However, in a short-lived program, leaking resources is not a big deal, because when the program stops running, of course, everything is cleaned up by the operating system. That's true of memory you've allocated as well as file descriptors. So if you don't allocate it, or don't free something or do at the end of a short-lived program, it probably doesn't make that much of a difference. Now sometimes you don't want to actually overwrite something. You want to write at the end of the file, like append to it. You might call that a log file, for example. And the way you would do that is you call this interface called lseek. And all lseek is doing is readjusting that hidden, where we're going to write to file position or file offset inside, the kernel in some open file table for this file descriptor. It's just adjusting it. And it lets you do that in a few different ways. You can see that you can use, for this whence argument, either seek set, seek cur, or seek end. And that affects how that offset argument that you pass to lseek is interpreted. If you say seek set, well, it sets the current offset to exactly the number you're picking. If you say seek cur, it takes the current location plus offset bytes. And if you say seek end, it says start at the end plus whatever the offset is. So if we're looking to append at the end, seek end makes a lot of sense with an argument of 0. And indeed, if we run this program again, under cat file 1, we have BA, and what we should have at the end of this is, of course, BAB. We've appended to the end of the file. And with lseek, lseek allows you to basically do random reads or writes within a file, right? When we saw the read stream that Cat was doing, it was just calling read repeatedly, and that's a very common usage to stream through a file sequentially, read the whole thing, or for example, write out a new file, write the whole thing. But if you're a database system, you need to look up a record, for example. You'll have to reposition where you're reading from, and lseek is the exact way you should do that. So that's writing. And of course, you could even position, and a very interesting thing you can do is you could open seek to the end plus, let's say, 16 bytes. So you can actually go past the end of the file by quite a bit, leaving some what you might think of as unwritten to space, which is a little bit weird. And in this case leads to a file that looks like that, but the reason it looks like that is because what got spaced in between there, this is 24 bytes, but this only looks like 2, 4, 6, 8 bytes, is what's in between there, what's in this kind of empty spot of the file is a bunch of zeros, which a C program takes as more like a, it's an end of string, so you don't really end up seeing it getting printed in any way. If you were able to basically dump out this file, you can see it actually has a bunch more stuff in it. This is the A and the backslash. This is the beginning. This is all the BAB, and then a bunch of zeros, and then finally one more B in this case. So in any case, you can write past the end of the file and have a file that actually has a bunch of holes in it. In this case, the file system will zero fill that stuff and leave you a file that looks like it's pretty big even though you haven't actually written to it. In fact, you can stat it. One thing command stat does is tell you something about the file. We'll look at that, and you can see a lot of things about it, including that it's actually 24 bytes. Okay, a little bit of an aside there. Let's get back into what we call truncate. Truncating is about making files smaller, an existing file. You can do that by explicitly calling the truncate system call, or in this case you can call open. This is a pretty common usage. I say I want to open this file for writing. If it doesn't exist, please create it. And if it does exist, please truncate it. Remove all the bytes from it because I'm going to write the file anew. So if I go ahead and do this compile trunc, you can see that works fine. You can see we cat file 1 to begin with. We call truncate. and we cat it. And at that point, we know that the file size is now 0, which you can see is actually the 5th argument of that ls list out there. So truncation works, and you can look at the system call truncate2 to give you slightly more control over removing parts of a file. For example, parts of a file. You can also just make it smaller as opposed to going all the way to 0, which is what happens when you call o_trunc. So let's look at file deletion. Nothing too exciting here. Well, except a little bit of a strange thing goes on here. And we'll make this the mystery of the day. Because when we looked at open, read, write, close, we can strace programs that do those. We now understand what's going on. Truncate's the same way. But to delete a file, you use this Unix command that's pretty typical. Some of you probably know it. It's called rm, remove a file. So then the question for you is, what system call is used by rm? Is it rm, just like when we said, well, what do we do to open? We open. To read, we read. To write, we write. To truncate, we actually truncate or open with the right flags. But for delete, it's not so simple. So let's look at exactly what happens when we go ahead and remove a file. Do our friend strace. Look carefully here. And you can see that the interface used, the system call used to remove a file is actually called unlink. And if there's anything else that you get out of this lecture about the file system API, hopefully at the end what we'll have is a really nice understanding of why unlink is the right thing to call when we want to delete a file, and not some sort of remove. And we'll make sense of that in a second, but it's just something for you to know right now. We also want to be able to rename files. To rename files, we actually use the command move. So let's say we have a file, file1. We want to rename it, so we say move file1 to file2. Then, yeah, we're going to overwrite file2 in that case. And let's remove some other files. Okay, let's do that again, just so we have nothing weird going on. And of course, if we do, see which files are around, we can see there's just file2 is there. We've just changed its name. And then we can do this again, and what we're going to do is use our friend strace to see again which system calls are used. And you can see actually there is a support explicitly for rename. Rename is a useful system call. It turns out to atomically switch the name of one file to another. And it turns out to be particularly useful in a number of places. In particular, when you want to, if your goal is to atomically create a new version of a file. Sometimes systems crash, and we'll talk about that more later. When they crash, what you don't want to do sometimes is leave a file in kind of an in-between state. Let's say you're editing an OS configuration file. And what happens is you're editing this critical file that's used on boot up in order to initialize the system with some parameters. You're editing it, the system crashes during that edit, and then it tries to boot up, and it gets a corrupt configuration file, and then it won't boot. So sometimes you really want to be able to say, I either want the old version of this file, or I want the new version. I don't want some in-between version. All file systems need to support this. So the basic way they do that is what you do is you open, say, the new some temp file, which is going to be your new file for writing. So let's say write only. And let's say we're truncating it too. And let's say we're creating it. Then what we'll do is we'll write out that file. So we'll fill it out with whatever the contents are that we want to write to it. Then we actually want to make sure that that file's on the disk. And there's a new interface to force writes to actually be committed to the drive. That's called fsync. Actually, you can pass it a file descriptor like that. what fsync does is it ensures, it's supposed to at least, it turns out that's pretty tricky too, it's some subject of current research, which is why I'm talking about it right now, ensures that writes to FD are now durable, which means they're on the disk. Once you have that new temp file on the disk, what you can do is you can issue a rename. And as you can see from renames, we should look up the system call, section 2, old path, new path. What we can do once we're done with that is we can say rename temp to what the original file is supposed to be called. And of course we do appropriate checking. And what the file system ensures at that point is that name change happens atomically, and so the old file becomes a new file. If we crash during this rename, the file will be left either in the old state with the old name or the new name, and that's okay. What the fsync piece implies is something very interesting. It's something you should definitely understand, and something we'll understand better when we talk about how file systems are implemented. But write does not immediately actually write to the disk or SSD or whatever. Instead, what happens is the OS buffers writes. This is for performance reasons. So I open a file, I do a bunch of writes, I even close it, even the process exits. It doesn't mean anything's been written to the disk. It just means the file system now has that information. If somebody else reads it, it'll give it to it, but that information generally lives in memory. Sometime later, in the background, the file system will write it out. If you want to change that, what you have to do is you have to do an fsync. Fsync allows the user to control this and say, okay, I really want this stuff to be on the drive, for example, because I'm about to do a rename, and I want to make sure that when I have the new version of the file, that it actually points to something that exists on the disk. Okay, now let's look at some things we've talked about a little bit already. Stat, this is how you get some info about a file. We saw this already when I did a stat on file 1. You can see here file 1's a bunch of information about it, and if you want to see what system call stat the user command program is using, well, not surprisingly, it's using, fstat. And in fact, there's 2 system calls that are pretty related, or actually 3, stat, fstat, and lstat. They all kind of do the same thing, just take a different first argument and then fill in this status buffer, which has all this information about a file. So let's look at file 1. Actually, let's go ahead and then echo something into it. And we can do this. We can just cat into file 1, say hello, and then we hit Control D, and we are done with that. Control D sends an EOF signal, and we know is interpreted as an end of file, and therefore we can stop filling in that file. We can, of course, then cat that file. We see that we get what we expect. And then we can stat that file and look at it a little bit. You can see it has size 6 bytes. You can see 8 4K blocks have been assigned to it. That's kind of interesting. 32K has been allocated to this file, even though we've only using 6 bytes, because what the file system's trying to do is be smart. It says, I want to make sure that this file has room to grow in case it does grow. So that's what it does. In this case, and this is probably an ext3 file system. So, yeah. So that's exactly what ext3 does. It's a regular file. We'll see in a short bit some different types of files. It has one link to it. We'll talk about what that means in a second. It's on a particular device. There are many devices attached to the system. It has different permissions for who can access, modify, and change it. And here is that we talked about files having a low-level name. For many reasons, the original Unix file system referred to each file by a number and called that the index or index number, and the index number was referred to that way because there was basically an array with one entry per file. We call the entry that stores this information about a file an inode or index node, and this is the index node's number. So that terminology still lives on today. An inode stores information about a file and is referred to by this low-level name, which is just a number. The type of information it stores is exactly what you see here. how big it is, how many blocks it has, a bunch of permission stuff. It also, of course, one thing it doesn't show here in the stat listing, but of course the file system tracks, is exactly which blocks belong to this file. And so if you could look inside the inode, you could see that too, but there's no interface for doing that directly. Okay, so that gets us basically most of the information we want about a file, how to access it, how to rename it, how to delete it with that mysterious call unlink, how to do most of the things. And we've actually developed a new concept. There's this thing called an inode, which holds what's called metadata for a file. Metadata is just information about the file, like its size, its how many blocks belong to it, where the blocks are, permissions, information, etc. And we'll talk a lot more about inodes when we talk about file system implementation. For now, we'll kind of forget about it at some level. Okay, so let's take one more break, come back and learn a little bit more about other file types, like, for example, directories.